Let's look to this topic, MOS Logic Family. From 2016 GATE onwards, in the GATE syllabus we are looking only MOS Logic Families. Before 2016 GATE exam, the GATE syllabus we were looking to the topics apart of the MOS Logic Families, the bipolar logic families, DTL, TTL and ECL. But these DTL, TTL and ECL, that is BJT logic families, are removed from the syllabus from 2016 GATE onwards. So in the MOS Logic Family, basically we are looking the implementation of the logic gates by using MOSFETs. So whenever we want to implement any digital system, if the NAND gates or NOR gates, it means if the universal logic gates are available, by using those universal logic gates we are having possibility to implement any digital system. Hence, whenever we are trying to implement the logic ICs with any active device, we will be trying to implement basically the universal logic gates, either maybe NAND gate or NOR gate. While we are implementing the NAND gate or NOR gate by using the active devices such as MOSFETs or BJTs, what it may be. Once we are able to implement the universal logic gates by using these active devices, by using those repetitive circuits, we are having in general possible to implement any digital system. So here also, if you look, by using MOS devices, we are trying to implement basically the NAND gate or NOR gate. So once we are trying to implement the NAND gate or NOR gate by using these MOSFETs, then we can implement any digital system by using these NAND gates or NOR gates. The MOS Logic Family, we can look further based on whether we are using NMOSFET or PMOSFET or CMOSFET. Based on that, we are having NMOS Logic Family, PMOS Logic Family and CMOS Logic Family. So in the case of this NMOS Logic Family, we are having the usage of N-channel MOSFET. We will be using here N-channel MOSFET. Whereas in the case of this PMOS Logic Families, we are having the usage of P-channel MOSFETs. In the case of this CMOS, we are having the usage of this both N and P channel. We are having both N channel and P channel MOSFETs. So when we are looking at comparison between the NMOS and PMOS logic families, generally this NMOS is preferable than PMOS. The reason is simple. NMOS logic ICs are having little fast speed than comparing with the PMOS logic ICs. It means NMOS logic ICs are having less propagation delay comparing with the PMOS. The reason, of course, if at all you are looking, we can speak based on the mobility of the charge carrier. In the case of this N-channel MOSFET, the majority charge carriers are electrons. The device operation is because of the electrons, whereas in the case of the P-channel MOSFET, the majority charge carriers are holes. The device operation is because of the holes. The electrons are having the larger mobility comparing with the holes. Having the larger mobility for the electrons, the switching speed will be less. So, propagation delay will be less. Switching speed is fast, the propagation delay is less for N-channel MOSFETs. Hence, most of the times we prefer to use this N-channel MOSFET when we are looking at comparison between the P-channel and N-channel MOSFETs. And if we come to the CMOS, it is a specific case. We are going to look into the due course. It is a special case. It is having its own advantage. We are having the usage of the combination of N-channel and P-channel MOSFETs. Let us work in the class right now with the NMOS. What is the discussion we will be giving for N-channel MOSFET? By using N-channel MOSFET, the implementation of the NAND or NOR, the same logic with small changes, the same circuit with small changes, we are having possibility to adopt even for PMOS logic ICs. Hence, let us start with the NMOS circuits. Here, well, using two MOSFETs, N-channel MOSFETs. This transistor T1 is called driver transistor. The transistor T2 is called load transistor. So basically the transistor T2 we are looking as a load of the transistor T1. So conventionally if at all we are looking, instead of this transistor T2 we are having a possibility to use a resistor. But instead of resistor we are having the usage of this N-channel MOSFET itself in the place of the load resistor. While using the MOSFET, the advantage what we are having in the IC form is MOSFET will take less silicon chip area comparing with the passive resistor. In the IC form, the MOSFET will take less silicon chip area comparing with the resistor, passive resistor. Hence, in the integrated circuits, wherever we are in need of the resistors in the MOSFETs, we are having the usage in the MOS Logic ICs. Wherever we are in need of the resistor, generally the resistor is implemented instead of passive component with a active device with the MOSFET itself. So it is the load of the transistor, it is the driver of the transistor. If you look to the operation of this circuit, let us look to the operation of this circuit in terms of the logic levels. If at all A is 0, we are looking the transistor T1 will be in the off state. Whenever the transistor T1 is in the off state, the output terminal to the ground impedance becomes infinite. So that why we are looking as plus VDD. This plus VDD in terms of the logic level we are looking as 1. Similarly, whenever A is 1, whenever input A is 1, whenever the input A is 1, the transistor T1 will be on. It is an N-channel MOSFET. It is an enhancement type of MOSFET. In the enhancement type of N-channel MOSFET, whenever the gate potential is 0, the MOSFET will be off. Whenever the gate potential is 1, the MOSFET will be on. So that whenever A is 1, the gate potential is 1, the transistor T1 is on. Whenever the transistor T1 is on, output to the ground, the potential becomes 0. So output to the ground, the potential becomes 0. The reason is because the impedance is 0. So we are looking here, the operation of this circuit is just as a NOT gate. Hence, it is a inverter circuit or NOT gate circuit. It is a inverter circuit or NOT gate circuit. So we are looking here, this transistor T1 is driver transistor, whereas the T2 is load transistor. As I said, instead of the passive resistor already, we are using a active device T2 MOSFET as a load to the transistor T1. So it is a NOT gate or inverter circuit. Let's look now the implementation of the NAND gate as well as NOR gate. So here we are looking circuit 1 and circuit 2. In both these circuits, the transistor T3 is load transistor. It is load transistor. Whereas the T1, T2 are driver transistors. They are driver transistors. Let us look to the operation of this circuit 1 and circuit 2 in terms of logic values. The circuit 1 output from the drain terminal of the T2 and circuit 2 output from the common drain terminal of the T1, T2. So in terms of the logic levels, if you look, on A and B, these are the possible values. If you look to the circuit 1 output, in the circuit 1, the transistor T1, T2, they are the driver transistors, they are in series. Among these two transistors, as long as at least one of the transistor is off, among these two driver transistors, as long as at least one transistor is in off state, then output Y will be plus VDD. Once the transistor at least one is off, means from the output terminal to the ground impedance is high, so output Y will be plus VDD. So we can see now from this table for the first three rows, from the first three rows we are looking at least one of the input is 0. Whenever at least one of the input is 0, then guarantee one of the transistor will be in the off state. Once from the transistor among the T1, T2 one is off, then output will be, as we said, plus VDD, that we are looking in terms of the logic level as a 1. And as and when transistor T1 and T2 both are on is possible whenever A and B both are 1. Whenever A and B both are 1, the T1, T2 both are on, hence output to the ground, the impedance is 0, so that Y will be logic 0. That is 0 potential we are looking as a logic 0. So we are looking to the circuit 1 operation similar to a 2 input NAND gate operation. So that the circuit 1 is NAND gate circuit. It is NAND circuit. Similarly, if we look to the circuit 2 operation, among these two inputs, if one of the input is 1, then one of the transistor will be on. Among these T1, T2, as and when one of the transistor is on, output to the ground impedance becomes 0 because T1, T2 are in parallel. As and when at least one transistor is on, output to the ground impedance becomes 0, so that Y becomes 0 potential, that is logic 0. So as long as at least one of the input is 1, at least one of the input is 1 for this, from this table if at all you are looking for this bottom 3 rows, as long as at least one of the input is 1, one of the transistor is guaranteed as on. Hence output Y will be logic 0. Whenever input A and B both are 0, whenever input A and B both are 0, the transistor T1, T2 both will be in the off state. When T1, T2 both are in the off state, then output Y will be plus VDD, that we are looking as the logic 1. So we are looking circuit 2 operation is similar to a 2 input NOR gate. Hence circuit 2 is giving the operation as NOR gate. So it's a NAND gate circuit, it's a NOR gate circuit. We are looking here in the NAND circuit implementation, the driver transistors are in series, whereas in the NOR gate circuit implementation, the driver transistors are in parallel. It is a way to remember. For NAND gate implementation, we need the driver transistors are to be in series, whereas for NOR gate implementation, the driver transistors are to be in parallel. So if you want a NAND circuit with 3 inputs, then definitely we are in need of using one more transistor as a driver transistor that is coming in series with this T1, T2. Similarly, if you want a 3 input NOR gate circuit, we need to use one more transistor as a driver transistor that will be coming in parallel with the T1, T2. So based on how many number of inputs are required, corresponding transistors are going to be connected in series for NAND circuit implementation, and corresponding transistors will be connected in parallel for NOR gate implementation. Here in this circuit we are looking, the transistor T1 is N-channel MOSFET. Transistor T2 is P-channel MOSFET. We are having the usage of N-channel and P-channel MOSFET combination here. Let us look to the operation of this circuit. Whenever input A is logic 0, whenever input A is logic 0, so they are basically gate potential to the transistor T1, T2. Whenever the gate potential is 0, the N-channel MOSFET will be in the off state, whereas the P-channel MOSFET will be in the on state. and from the output terminal to the ground impedance is high, so that output will be logic 1. And whenever input A is 1, then N channel MOSFET will be on and P channel MOSFET will be in the off state. Whenever N channel MOSFET is on, from the output to the ground impedance becomes 0. Whenever the impedance is 0, output will be logic 0. So that we are looking to the operation of this circuit as a NOT gate. Hence, it is a inverter circuit. It is a inverter circuit. Here we are having the usage of both N channel and P channel MOSFET. Based on this, we are naming the circuit as a complementary metal oxide semiconductor field effect transistor. So this CMOS circuit is giving the operation as a inverter circuit. It is giving the operation as a NOT gate. The comparing with the N channel logic family ICs or P channel logic family ICs, the advantage of this CMOS logic ICs is the power consumption of the CMOS logic family ICs is less comparing with the NMOS or PMOS logic ICs. The power dissipation, generally we are having a calculation as the supply voltage into the current drawn from the supply. So supply voltage into current drawn from the supply. From the current drawn from supply, if at all we are looking this ID current from the supply to the ground, among these two transistors we are looking guarantee always one of the transistor is off. Among these two transistors always we are looking one of the transistor is always in the off state. Once when the transistor is in the off state, the current drawn from the supply is always less, which makes the power dissipation is less. Once the power dissipation is less, means the power consumption is less. So it is a major advantage of the CMOS logic ICs. So wherever we are having remote application, the remote application power usage is very critical thing. The battery what we are using, if at all it is going to be used for a long period of time, if the aging of the battery is long, it is going to be an advantage. Particularly for remote applications, frequent replacing of the batteries is not possible. So in such places, definitely these CMOS ICs are preferable to use. Or modern days, whatever the cell phones we are using, in those cell phones, whatever the battery we are having, if at all it is used for a long period of time, it is going to be an advantage. The battery aging will be improved if at all we are having the usage of such CMOS logic ICs. In this CMOS logic ICs, also logic families also are having possibility for the implementation of the 9 circuit as well as the NOR circuit. Let us look to the 9 gate circuit as well as the NOR gate circuit. So here we are looking to circuit 1 and circuit 2. In the circuit 1 and circuit 2, T1, T2 transistors in both these circuits are N-channel MOSFETs. Based on the symbols, we can see they are N-channel MOSFETs. Whereas T3, T4 transistors in both these circuits are P-channel MOSFETs. And also we can look, transistor T1 and T3 is one pair. T1, T3 is one pair in both the circuits. T1, T3 is one pair. And also T2, T4 is another pair. T2 and T4 is another pair in both these circuits. Let us look to the operation of this circuit 1 and circuit in terms of the logic levels. Whenever we are looking to the possible values on A and B, these are the possible values on the input binary variables A and B. Based on these possible values, let us look first the states of the transistor T1, T2, T3 and T4. If A and B both are zeros, whenever A and B both are zeros, N-channel MOSFETs will be off state in both the circuits, of course, will be in the off state. And P-channel MOSFETs will be on state. And whenever A is 0, A is the input to the T1. So the T1 transistor will be in the off state, so that T3 will be in the on state. And whenever B is 1, that is the input to the transistor T2, that is the gate potential to the T2, so that T2 will be on state, hence T4 will be off state. Similarly, whenever A is 1, T1 will be on state, T3 will be in the off state, and when B is 0, T2 will be in the off state and T4 will be in the on state. When A and B both are 1, T1, T2 both are on, so that T3, T4 both will be off state. So based on the A and B values, these are the states corresponding to the transistors T1, T2, T3 and T4. Now, based on the states of the transistors, we can look to the circuit 1 as well as the circuit 2 outputs. Let us look first the circuit 1, output Y. So Y of the circuit we are taking from the transistor T2 drain terminal. So among the transistor T1, T2, at least one transistor is off. Among the T1, T2, at least one is off. Output Y will be plus VDD. Among these T1, T2, at least one is off, means the output to the ground impedance is high. Hence the output will be plus VDD, that we are going to read as a logic 1. So you can look here for the first 3 rows. From the first 3 rows, guarantee at least one transistor is in the off among this T1, T2. So once when the transistor is off, output will be plus VDD, that we are looking as the logic 1. As we know, as I said already, this is one pair, this is another pair. And whenever T1, T2 both are on, whenever the T1, T2 both are on, then output will be logic 0, because output of the ground impedance is 0. It is 0. So we are looking, the operation of circuit 1 is a 2-input 90 gate operation, so that the circuit 1 is 9 circuit. Similarly, if you look to the circuit 2 operation, among the transistors T1, T2, at least one transistor is on. At least one is on means output to the ground impedance is 0, output will be logic 0. For the bottom 3 rows, we are looking among the T1, T2, guarantee at least one is on. Whenever one is at least one is on, we are reading output will be logic 0. And for first row, T1, T2 both are off. When both are off, output will be plus VDD, so that output Y will be the logic 1. The circuit 2 is giving the operation of a 2-input NOR gate. Hence, the circuit 2 is NOR circuit. So we are having circuit 1 operation as a 9-gate circuit. Circuit 2 operation is NOR gate operation. The 9 circuit implementation, we are looking N-channel MOSFETs are in series and the P-channel MOSFETs are in parallel. That is in the case of the 9 circuit implementation. Whereas in the NOR circuit implementation, N-channel MOSFETs are in parallel and the P-channel MOSFETs are in series. We took here the discussion of the 2-input logic gates, 9 and NOR gate. If we want more than 2 inputs, we want 3 input, then definitely here one pair is going to be added. One must be N-channel, other will be the P-channel. So N-channel will be in series with the T1, T2, P-channel will be in parallel with the T3, T4. Similarly, for NOR gate implementation, N-channel MOSFET will be in parallel to the T1, T2 and the P-channel MOSFET will be in series with the T3, T4. So hence it is possible for us to have even more than 2 inputs, 3 input, 4 input, 9 circuits or as well as the NOR circuits. These are the basic circuits of the 9 circuit NOR circuit. So here we discuss MOS logic and CMOS logic. If you want to have the PMOS will be very similar to this NMOS, very similar to this NMOS with small changes. So in the place of NMOS FETs, we are having the usage of PMOS FETs and correspondingly will be having the change in the supply voltages. But the basic circuit of NMOS logic IC and PMOS logic IC will be same. The MOS logic ICs in general are having high fan input. Fan input is high because we are looking for MOS ICs, input impedance is more, having input impedance is more, the fan in is possible to be high. And fan out also high. And power consumption is less. Power consumption will be less. And component density is more. Component density is more. And they are cost wise cheap. They are cheap. The cost of the logic ICs is less. These are the advantages of the MOS logic ICs comparing with the bipolar logic family ICs. In fact, as per the syllabus, we should not talk this because no bipolar logic family ICs. So no need to, no, it's not possible to compare, but as a matter of discussion I am mentioning here. In general, if at all we are looking, the MOS logic ICs are having high input impedance. Having high input impedance, the fan in and fan out both will be large. And of course, in general, if at all you are looking, the power consumption of the MOS logic ICs will be less. And among this NMOS and PMOS and CMOS, among NMOS, PMOS and CMOS, among this power consumption is less for CMOS. Is less for CMOS. In general, MOS logic ICs are having less power consumption. Among these three, if at all you are looking, CMOS is having less power consumption. And of course, component density is possible to be high. Based on this, the cost per gate will be less. So they are cheap in the cost. These are the advantages in general for these MOS logic families. So let us look to this question. What is the Boolean expression which is implemented by this MOS circuit? What is the Boolean expression which is implemented by the MOS circuit? You can see here, the transistor T1 is in parallel with the combination of T2 and T3. And this for T1, T2, T3, the transistor T4 we are looking as the load. So if you look, what is the Boolean expression which is implemented by this circuit? It is possible to write expression Y as transistor T1 input is A. A is in parallel with the transistor T2, T3 combination. T3 and T2 inputs B and C respectively. So that A or B, C. And it is a load, hence it is a complement operation. Hence the Boolean expression which is implemented by this circuit will be A or B, C. It is one of the gate exam question. We'll be having some options like this. One option will be A or B, C. One option will be A and B or C. One option will be A or B, C complement. One option will be A or B or C whole complement. Then definitely the answer will be option C. The answer is option C. So definitely the answer is option C. Let us take this another question. What is the Boolean expression which is implemented by this MOS circuit? In the MOS circuit, the given MOS circuit, all the FETs are N-channel MOSFETs. We need to recognize what is the Boolean expression which is implemented by this circuit. We are looking here, the transistors corresponding to this A and B inputs, these two transistors are in parallel. Whereas these two transistors which are corresponding to the input C and D are in series. And we are looking this transistor, of course, it's a load to the total circuit. So we can look, whenever these two transistors are in parallel, it becomes OR operation, and these two transistors are in series, so it is AND operation. And these two blocks, we can look here, it is one block and this is another block. They are in parallel combinedly, so that OR operation. And because of this load, it is total complement. Hence, the Boolean expression we are looking, which is A or B, or with CD whole complement. So the answer is option D. Answer is option D. It is also one of the previous gate examination question. Try for one more question. What is the Boolean expression which is implemented by this MOS circuit? So if you want to identify what is the Boolean expression which is implemented by this MOS circuit, you can see based on the circuit, this transistor will be the load transistor and the remaining all are the driver transistors. And we are looking here Q and R corresponding transistors are in parallel, and it is combinedly in series with the transistor which is with the input of P. And these transistors, they are corresponding to the inputs of C, S and T are in series. And this block is in parallel. Based on this, if you read the output expression Y, so let's start from this. It is Q R with R in series with the P in parallel with the S, T and whole complement. So that the answer to this question is the Boolean expression Y is equal to P and with Q R with ST whole complement. It is the answer for this question. In the memory topic, we need to discuss very briefly about few of the memories. Very briefly, because it is not having such importance in the GATE exam. You can look the memory, you can look primary memory, the and secondary memory. Under the primary memory, generally we are looking to the semiconductor memories. The semiconductor memories are the primary memories. And in the secondary memory, we are looking to the magnetic tape, hard disk, etc. These are considered to be the secondary memory. And coming to the semiconductor memory, for the semiconductor memory, we are looking to the memory as one memory, random access memory, other memory is read-only memory. In the case of this random access memory, we are looking, it is volatile memory, whereas this read-only memory is non-volatile memory. It means for the data we are writing, the data will be available even the power is off in the case of the non-volatile memory. Whereas in the case of the volatile memory, once the power is off, earlier content is no more available. And in the case of this random access memory, we are having the possibility of both read and write operations. So user can write and read the data from this random access memory. Whereas in the case of the read-only memory, for the end user, the possibility is only read operation. We are having a possibility of only read operation. So write operation is not possible by the end user. And one other thing about the random access memories and read-only memories is random access memory is sequential circuit, whereas the read-only memory is combinational circuit. So in the case of the random access memories, in general, if at all we are looking, the one memory cell is implemented by using a flip-flop. Once we are having the usage of flip-flops, then it becomes an example of a sequence circuit. Whereas the read-only memories are concerned, they are implemented with a combination of the decoder and encoder. So because of usage of the decoder and encoder, the read-only memory becomes the combinational circuit. So these are the few major differences we can see among these random access memories and read-only memories. And if you look to the little more details about these read-only memories, as I said, the read-only memory is basically implemented the combination of the decoder and encoder. So the decoder outputs are the inputs to the encoder, and decoder inputs are the inputs to the overall circuit, and encoder outputs are the outputs to the overall circuit. So this combined block we are naming as read-only memory. The read-only memory, we are having a possibility, if at all we are looking at the applications, we are having a possibility to use to implement a combinational circuit. We are having a possibility to implement a combinational circuit. For example, we are trying to implement, say, a BCD to XS3 code converter. If at all we are having implementation of this BCD to XS3 code converter, the inputs will be here now, this BCD data D, C, B and A. Whereas output will be this XS3 code E3, E2, E1 and E0. So what is the functional relation we need between the output and input? They are implemented in this encoder block. So the masking will be done in this encoder block by the manufacturer. Early days it is to be done by the manufacturer. And if you look to the few other applications, we are having a possibility to use the read-only memories as lookup tables. You can use the read-only memories as lookup tables. So lookup tables are nothing but the logarithmic book. You can take an example. So if at all we are having the implementation by a read-only memory, in particular read-only memory for implementing, say, a sine function, a argument will be given here, the angle value will be given, and sine of that angle will be provided here. So that function relation what we need between the output and input, that is implemented by this in this encoder block. And we are having the possibility to use as sequence generator. We are having possibility to use as waveform generator. These are the few important applications what we can see with this read-only memories. Early days, the manufacturer is to implement the functional relation between the output and input in this encoder block. So it was done by the manufacturer when the chip was fabricated. But later time, because of the technology improvement, we are having the read-only memories. We are looking to the read-only memories further as programmable read-only memories. We are looking these read-only memories further as programmable read-only memories. So in the case of this programmable read-only memory, by the designer, programming is possible. The programming here, it is nothing but hardware programming. Hardware programming is nothing but implementing the hardware relation between the output and input in this encoder block that we are naming. So this programming is possible only single time by the manufacturer. Later time, we are having the memories with the name of erasable programmable read-only memories. In the case of this erasable programmable read-only memories, we are looking erasing operation and reprogramming operation is possible by the designer as many times as he needs. So erasing is possible. Erasing is possible maybe by exposing chip to ultraviolet radiation. So exposing chip to ultraviolet radiation around 20 to 30 minutes, with this erasing operation is possible. And in the case of other erasing, by sending current signals, erasing is possible. So if at all we are having the erasing operation by exposing chip to ultraviolet radiation, this we are naming UV erasable programmable read-only memory. If at all we are having erasing operation by sending electric signal, it is named as electrically erasable programmable read-only memory. Electrically erasable programmable read-only memory, for this case, the erasing will not take much time. It is a matter of few milliseconds or microseconds. And possible here, in the case of the electrically erasable programmable read-only memory, the erasing operation is possible even at bit level. So if you want, you can erase a particular bit value. If you want, you can change a particular word value. If you want, you change a group of words. So erasing is possible even at the bit level. Whereas UV prompts erasing is not possible like that. Once a chip is exposed to ultraviolet radiation, the total content will lost. And here, what is the programming we are talking? It is hardware programming. Hardware programming is done by the either manufacturer or maybe by using this erasing operation by the designer in this encoder block. So programming is nothing but hardware implementation, hardware relations implementation in this encoder block that we are naming as erasing programming. It is not conventional software programming, it is hardware programming. And we are looking further in this semiconductor memories further, static memories and dynamic memories. Static memory and dynamic memory. In the static memory, once we are writing the data is available as long as the power is on. Whereas in the case of the dynamic memory, even the power is on, the data is not available for a long period of time. The data will be not available for a long period of time. So why it is so, if at all you are looking, basically the static memory is implemented, cell implementation is the flip-flop concept. Cell implementation is with the flip-flop concept. Whereas here cell is implemented, cell implementation is the MOS capacitor. Cell is implemented with the MOS capacitor. So once is the MOS capacitor, it is possible to look. Once the MOS capacitor, it is possible to look. Once we are writing the data is nothing but capacitor is going to be charged to certain voltage value. The capacitor will be holding that voltage for a small amount of time. After certain time duration, the capacitor, because the parasitic elements, it is going to discharge. So before discharging to certain logic level 1 or logic level 0, it is to be recharged. If at all it is not recharged, the content will be erased. Content is no more available. It is a basic difference what we are looking between the static memory and dynamic memory. The static memory cell is implemented by using flip-flops, so that once we are writing the data is available for a long period of time as long as power is on. In the case of dynamic memory, the data is not available for a long period of time or even the power is on. The reason is cell is implemented with the MOS capacitor, the capacitive action of the MOS device. And you can see further differences between the static memory and dynamic memory as so cell implementation, the flip-flop, cell implementation with the MOS capacitor. This is the thing what I discussed. So the data is not available for a long period of time. Because of this, frequent re-rating operation is required in the case of the dynamic memory. Frequent re-rating operation is required. Frequent re-rating operation is required. Such a frequent re-rating operation is not required in the case of the static memory. And static memory cell is implemented using maybe bipolar junction transistors or maybe by using MOSFETs. So we are having the static memory implementation possibility maybe by using BJTs or maybe by using MOSFETs. Whereas the dynamic memories we are having possibility to implement by using only MOSFETs. And a single cell is implemented by using 6 transistors, whereas here single cell is implemented by using only 2 transistors. It is one of the important thing. It was a question couple of times in the GATE exam or in many competitive examinations. static memory cell is implemented by using 6 transistors, whereas the dynamic memory cell is implemented by using only 2 transistors. Based on this, we can talk few of the advantages. While using the lesser transistors, definitely the component density is more. Component density is more comparing to this. Comparing to the static memory, here for dynamic memory component density is more, and power consumption is less. Power consumption is less, and definitely it is making cost of the memory will be less. All these are considered to be the advantages. Because of the lesser transistors usage, definitely the supply voltage, the battery usage will be less. Hence, the battery will be used for a long period of time. So, we are talking the power consumption is less. So, operational expenditure is coming to be less. While having more component density, single transistor is implemented, lesser transistors comparing to this. So, having more component density, definitely the cost per gate, cost per cell will be less. So, these are considered to be the advantages of the dynamic memory over static memory. And coming to little about this secondary memories. Coming to this secondary memories, this magnetic tape and hard disk, these are sequential access memories. These are sequential access memories. It means, suppose, better example with the magnetic tape we can look. We are having one word at this location A, other word at this location B. Definitely the access time to the location, if at all consider, we are having read-write head somewhere here. Then access time to this location A will be less comparing to the access time to the location B. So access time is not uniform in the case of this sequential access memories. The magnetic tape and hard disk will be coming to be an examples of this sequential access memories. Whereas semiconductor memories, as we said, primary memories, semiconductor memories are random access memories. It means the access time is uniform for any location. Here the access time is uniform for any location, whereas here the access time is not uniform for any location. And semiconductor memories, you can see further, the semiconductor memories are generally, we can consider the examples of as non-volatile memories. They are non-volatile memories. So what is the data we are writing? That is going to be available for a long period of time. Even the battery is off, power is off, also the data content is possible to access. So it is coming to be non-volatile memory. So these are the few basics about these memories. So generally the scope of the gate exam will be within this range. At all we are looking at the PLDs, programmable logic devices. In this programmable logic devices, we are looking 3 categories. One is programmable read-only memories, programmable array logic, other one is programmable logic array. In the programmable read-only memories, the programming, that is hardware programming is in the encoder block. It means the programming is on OR gates. Whereas in the case of the programmable array logic, the programming is on AND gates. Whereas in the case of the programmable logic arrays, the programming is possible both AND and OR gates. The programming is possible both AND and OR gates. So programming is nothing but implementing hardware function. Here it is in the case of this AND gates as a minterm, as a product you can say here, or operation providing. So this is one thing we need to bother about these programmable logic devices. In the case of the programmable read-only memories, the programming is with OR gates. In the case of programmable array logic, the programming is on AND gates. In the case of the programmable logic arrays, the programming is possible both and OR gates. Okay, this is related with the programmable logic devices.